Hello, eighth graders. Today we are going to talk about the revolution of Earth. Yesterday we talked about how Earth rotates on its axis once every 24 hours and that our axis is tilted 23 degrees. Okay, while we're rotating on our axis, we are also revolving around the sun, just like all of the other planets do. Even though our planets are very, very different, you can see that from this picture here. This is a picture of Saturn. It is one of the, it's the second largest planet in our solar system. What makes it so massive are the diameter of these huge rings. And actually, all of the gas giants, all those four outer planets, Jupiter, Saturn, Uranus, and Neptune, they all have rings because they're so big that shrapnel from space gets kind of sucked in by their gravity and all of that stuff kind of starts to orbit the planet and collect over time. But Saturn is the only one that has such a big ring system that we can actually see it through a telescope from Earth. The other three gas giants, you cannot see that feature. Look at how teeny tiny Earth looks in comparison. It's quite amazing. I would say for purposes of comparison, Saturn would be like a dodgeball and Earth would be like a quarter. No, a nickel. Okay, so quite a bit different in sizes. Certainly no one today doubts that Earth orbits a star, the sun. We have lots of pictures that are taken from space. There's been a lot of observations made by astronauts. We've had a lot of space exploration that depends on that understanding. And all of that stuff confirms it. But we did not always think that way. We did not always have our current understanding. And actually, in the 17th century, if you were to say that Earth revolved around the sun, you would be booted out of the church and charged in a court for going against God and be thrown into house arrest for the rest of your life, which is what happened to the father of modern science, and his name was Galileo. Okay, so we'll talk about Galileo in just a little bit, but let's back up. Let's back up to back in the day. We're talking about BC times, again, when people were walking around wearing togas and flip-flops, the times of some of the ancient Greek and Roman philosophers, okay? They believed in something called the geocentric model of our solar system, actually of the universe, because they did not have a grasp on how vast the universe was. They really believed at that time that what we saw in the sky was it. That's it. And because they couldn't feel like they were moving, right? They were standing here. We don't feel like we're moving. And because they saw with the only tools they had, they didn't have telescopes yet, they saw the sun come up in the east and set in the west every day. They saw the stars move across the sky every season, and throughout the evening, they made the conclusion that Earth is stationary and all of the things in our solar system revolve around that. And that aligned with religion at the time. Okay, and religion was law back in those days. There was no separation there. Okay, so to go against a model like this, to say that this model of the universe was wrong, was to go against the church, right? In their statements, God made this perfect earth and everything therefore should revolve around it. That was kind of their line of evidence. Okay, so this first geocentric, geo means earth, centric, centered, earth-centered model. We had each object in the sky was attached to a sphere and moves around the earth as that sphere rotates. Okay, so it'd be like here's my Sensi pot here. Here's the earth, and then there was all of these rings around it. kind of like a vinyl record, as though, if you know what that is. I don't think you do. And those, what they were saying was that these spheres, these circular orbits, moved around the Earth with the planet attached to it. It says, since the planets appear to move much faster than the stars, the Greeks placed them closer to the Earth. Okay, so they also believe that all the stars were attached to an orbit and revolving around the Earth. And again, it wasn't because these guys were a bunch of dummies. They were really brilliant people, right? It's just that they didn't have the tools that we have now, or even that we had in the 1600s, to be able to make observations with anything other than their eyes, all right? One big problem with this geocentric model was that some planets seemed to move backwards during parts of their orbit, okay? And we call that retrograde motion, okay? So what they're saying is that from Earth, you could see, for instance, Mars, and this happens with Mars every 23 or so months. Mars is rotating, and then it goes backwards a little bit, and then it rotates, and then it goes backwards a little bit, okay? We know now that that is because we are moving at different speeds. So sometimes Mars is ahead of us while we're revolving around the sun, and sometimes we pass up Mars, and it appears that Mars is going backwards. But they didn't know that at the time. Remember, they thought everything was revolving around the Earth. And so the first guy that was credited with actually drawing a diagram that was accepted for more than 1,000 years of the geocentric model was a guy named Ptolemy. The P is silent here, Ptolemy. He resolved that problem by using something called epicycles. They're like little circles within circles. So now this diagram is getting really complicated. Okay, so looking down here, he said that the Earth was in the center and that planets were attached to these spheres to make them revolve around it. And then within those spheres, they were also attached to these other little circles. So they're cruising around on their little circles as they were cruising around our planet. And they said that that was true for all the planets and the stars. Widely accepted. Again, for more than 1,000 years, widely accepted. All right. Until a Pollock came along. Yay, Pollocks. Okay, so the beginning of the 16th century, a man named Nicholas Copernicus proposed that Earth and all of the other planets orbit not the Earth, but the sun. Okay, and so now he's come up with this helio meaning sun-centered model. So now the sun's in the middle, and all of the planets are revolving around it. Okay, although Copernicus's model was simpler, it didn't need these little epicycles or anything, it still did not perfectly describe the motion of the planets because it had the sun in the center and then these perfect circles going around where all of the planets were. And that still didn't explain what they were seeing, okay? Because sometimes we appeared to be further from the sun than at other times. And so there was still something a little bit fishy about this model. And at that time, Kepler came along, okay? And so this was fairly close together. These two discoveries were fairly close together. Johannes Kepler was a German mathematician. He took the information from Copernicus. He took Copernicus's model of the sun in the center and all of the planets, and he came up with what we now know as the laws of planetary motion. You can get a book on the laws of planetary motion. It's this big. It's really dry reading. I don't recommend it, but I will paraphrase it for you. What he said is that all of the orbits are not circular. They are actually ovals. They are elliptical, okay? And that the sun is at one side. There's not a center to an oval, right? There's not an equidistant center. And so what you have are two centers. They're called a focus and a focus, or plural foci, all right? Meaning if there's an oval and you've got these two foci, this distance is equal to this distance, which is equal to this distance, and this distance, and this distance, okay? And the sun is at one of those sides. And so while we are revolving around the sun, there are times when the gravity of the sun kind of shoots us around a little faster, and times where we're slowed down a little bit, and sometimes where we're faster, okay? So Kepler's laws of planetary motion helped explain a lot of what Copernicus was trying to say, okay? So Copernicus didn't really get into trouble for saying this. He came up with the idea, but he didn't go knocking on anyone's door saying, hey, y'all, you're wrong. He just proposed this, and Kepler helped to refine that idea. Well, now we're into the 17th century, and Galileo Galilei, he's a very famous dude. He's actually mentioned, right, in Bohemian Rhapsody, right? You guys know that song by Queen. He, known as the father of modern day science today, he's credited with that because he's the one that took these models and said, we need proof. You can't just come up with this stuff. Where are you guys coming up with this stuff? And so he didn't discover the telescope, but he refined the telescope, and he used the telescope to actually make direct observations. And what he noticed, one of the first things that he discovered when he looked through his telescope were the moons of Jupiter. Now, obviously, his telescope was not as powerful as the ones we have now. Okay, so Jupiter has like 73 moons. He found 4 of them, the 4 biggest ones. The 4 biggest moons of Jupiter, which you can see through a normal household telescope, are known today as the Galilean moons. And that is because he discovered them. And he said, hey, I'm looking right at them, everybody. These moons are revolving around Jupiter. There are things that revolve around things, not just Earth. And so he took all of this information and he came up with a more accurate depiction of our solar system and said, by the way, our solar system is not it. There's a universe out there. We are a small piece of that. He brought it to the people, and they did not like it at all. And they said that he was going against God, and he was charged with heresy, and he was locked in his house on house arrest for the rest of his life. And they would not publish any of his writings for the rest of his life. It wasn't until after he died, and this is actually common back in those days, and even sometimes today, where after somebody dies, we're like, oh, whoopsie. Sorry about that, man. Turns out you were right, and now we're going to publish all your books, and we're going to glorify you and give you the name of father of modern day science. Hooray for you. Sorry about your luck with the last part of your life being locked in your house. But his discoveries caused many people to accept the heliocentric model of the universe. Although Galileo himself was found guilty and locked away, the shift from the Earth-centered view to the sun-centered view of the universe is referred to as the Copernican Revolution. Okay? So again, Copernicus was that first guy that kind of suggested that the sun is the center and that we all revolve around it. Kepler explained it with mathematics. Galileo took all of that and drove it home and said, this is how it is. And he got into some big trouble for it. All right, so here's our heliocentric model. Again, showing Kepler's model that they are elliptical orbits and that the sun is off to one side. Therefore, there are times during the year that we are closer to the sun than others. And recall this month in January, we were at our perihelion on January 2nd, meaning we were closest as we ever get throughout the year to the sun on January 2nd. Pretty cold that day. Kind of odd, right? You'd think that we would be closest to the sun sometime in July or August, but actually that is when we are at our aphelion, which is when we are furthest away. And we'll learn that it isn't distance, it's tilt that has to do with our seasons, and that is our next chapter. All right. Okay. In their elliptical orbits, each planet is sometimes farther away from the sun than at other times. This movement is called a revolution. Okay, not to be confused with rotation. Remember, rotation is to spin on an axis. To revolve is to move around another body in orbit. Okay? At the same time, Earth spins on its axis. The Earth's axis is an imaginary line passing through the planet's center, goes right through the North and the South Pole, and that spinning motion is called the rotation. All right. So Copernicus, Galileo, and Kepler were all right in their own ways. Earth and the other planets travel in elliptical orbits around the sun. The gravitational pull of the sun keeps those planets in orbit so that we don't go flying off, right? According to Newton's laws, an object in motion should stay in motion along the same line, right? So this planet could just go flying off into space. Well, we're all kept in this clockwork because our sun is pulling at us. And we'll also talk about how some of the outer planets, some of these really big daddies out here, Jupiter and Saturn, they have a gravitational pull too. And so they're pulling away. They're pulling, if Jupiter suddenly got, I don't know, vaporized somehow and went away, these inner planets would go flying into the sun, right? It's a perfect clockwork of planets and gravitational pull to keep us where we're at. And it wasn't like it just plopped down perfectly. There was all kinds of shrapnel in here when our solar system first formed. There was all kinds of stuff, and it either got sucked into the sun by its gravity or pulled into one of the bigger planets by their gravity or shot out into space. And so this is what is left over, okay? This is what is left over after our solar system cleaned house and cleaned up the space by pulling and pushing things around. Alrighty? Well, we've got one question. I'm going to post a 2-minute video about some early astronomers, and my question to you is going to be about the difference between the heliocentric model and the geocentric model. And tomorrow we will be talking about seasons. I'll talk to you then.